Now I'm going to start a review for chapter 3. Remember, this is a really long chapter, did a lot of different types of problems. So the unit is just going to be chapter 3. All right. I don't want your brains to blow up from all these problems and add another chapter to it. So chapter 3 is the unit 2. So after we're done with this, then it's time for you to take another test. Okay. All right. So remember, we did conversions. We took moles and changed it to grams, atoms, and so on. So I have some examples here. Remember, the first thing you need to do is write down what you know. I have 0.436 moles of ammonium chloride. Okay, so what I'm going to do is I'm going to put moles on the bottom, and 1 mole of ammonium chloride, this is its mass. And again, you can get that from the app on your phone, or you can figure it out if you don't have the app. But all I have to do here is moles cancel out. I have grams left over. So this times this. So when I have 0.436 moles of ammonium chloride, it's 23.33 grams. And most of the times you'd have to convert it to that because I can't measure out moles, but I certainly can measure out grams. Okay. Here's where I'm starting with moles, and I'm going to change it to grams. So again, write down what you know. 0.25 grams of water. Okay. I know that 1 mole of water has a mass of 18. Again, that's 2 hydrogen, 1 oxygen added together. So on this one, instead of multiplying, I want my grams to cancel out, so that's why it goes on the bottom. So now I'm actually going to divide. And yeah, you're going to get a kind of a small number, but that makes sense because you don't have very many grams. So 0.014 moles of water in 0.25 grams. Okay. We also talked about molecules and atoms and so on. Remember, that's that magical number, Avogadro's number. When I was in school, we called it Avogadro's number just because, we had to be weird. But anyway, remember the number of molecules in a mole, the number of atoms in a mole, it all equals Avogadro's number, 6.02 times 10 to the 23rd. And that was mathematically figured out because you can't count that high, okay? Not in your lifetime anyway. So again, write down what you know. 1.2 moles of carbon dioxide. You don't have to find the mass of carbon dioxide. Not needed. Put your moles on the bottom and Avogadro's number on top. So you're just going to take this times this and then tack on your 10 to the 23rd. So when you take 1.2 times 6.02, you get 7.22 and then times 10 to the 23rd. So that's how many molecules there are in 1.2 moles. It would be of anything. It doesn't have to be just carbon dioxide, but of any substance, that's how many molecules you would have. Okay. Sometimes we got to go from grams to molecules, and that's a two-stepper because we don't have a direct conversion. So again, write down what you know. I know that I have 79.9 grams of sodium hydroxide. That's what it tells me in the beginning. I want to get rid of grams. So 1 mole of sodium hydroxide has a mass of 40. And again, that's 1 sodium, 1 oxygen, 1 hydrogen. It's just its mass. So now I get rid of grams, but I have moles and I want molecules. So 1 mole, and again, 1 mole of any substance has Avogadro's number of molecules. So now to solve this one, I'm going to take this times this, and I'm going to divide by this. So 79.9 times 6.02 divided by 40, and then tack on 10 to the 23rd. Well, you get 12.02 when you multiply all these things together, okay? You can't leave it like that, you guys. That's an improper scientific notation. So what I'm going to do is I'm going to move this decimal over here. I'm going to make this number smaller, so I'm going to make this number larger. So 1.2 times 10 to the 24th molecules in 79.9 grams of sodium hydroxide. Okay, so make sure you write in proper scientific notation. Okay, here's some equations. I'm not going to balance them. I'll show you some tricks to balancing them, but make sure you know how to balance equations, how to write equations. There's all kinds of videos on it. I have some videos that I already uploaded for you. It's just one of those things. Remember, this half and this half have to have the same amount of substance. So if there's 6 silver over here, there has to be 6 silver over here. This one, the problem is right there, that NO3 group. So I'm going to put a 2 there, and then I'll put a 2 there, and we're all good. Okay. Anyway, but the types of equations. Okay. Remember to look at, how many parts. Here I have 2 reactants and I have 2 products. So I know it's either single or double replacement. As long as these aren't carbon dioxide and water, it's not combustion. So it's single or double. And I look, I got no elements by themselves, so this is a double replacement. The silver goes with the chlorine and the calcium goes with the nitrate. Okay. On this one, I start with 2 and end with 2, so that's also either going to be single or double. Now I look for elements by themselves. Here I have sodium by itself, I have hydrogen by itself. So basically, sodium kicks out hydrogen. Sodium replaces it. So this is just a single replacement. Okay. On this one, I start with one reactant and I end up with two products. So I broke it down. When you break things down, that's decomposition. Okay. So you see the difference. This has two reactants and two products. This has one reactant and two products. So I know this isn't single or double replacement. So I look at it and it broke down. Break down means to decompose. Here I have two substances and I add them together to form one. Okay, so now I have two reactants and one product. So these two are opposites of each other. This is synthesis or combination. They're combining. I'm making something. This one I'm breaking it down. Okay. Here's some more. Again, look at this. I got 1, 2 reactants and I have 3 products. So I must have broke some of this down. So that's decomposition. So it doesn't have to be 1 broken down into 2. Here it's 2 broken down to 3. It can be 2 broken down into 5. Just as long as you end up with more parts than you start with, that's decomposition. Okay. This one's combustion because I have carbon dioxide and water. This is like the big red flag. Here we go. Combustion, combustion, combustion. Okay. When you're balancing a combustion reaction, they're probably the hardest ones to balance. But if you follow a little trick, they're not so bad. Okay. So you take and you balance your carbon first. So I put a 4 here. And then you balance your hydrogen. And this is 10. So I need to put a 5 here. Well, the problem is I got 8 and 5. That's 13. I can't get 13 over here because I have an even number. So if you end up with an odd number over here and an even number here, the trick is put a 2 right here and then start over. So put a 2 here, make this 8, put an 8. This is 20, so I put a 10. So now I have 8 times 2 is 16, plus 10, 26. So now I put a 13 right here. Okay, so anytime you're doing a combustion, start with a carbon, then do the hydrogen, save the oxygen for last. If you add an odd number over here and an even number over here, double the first one, and then it's not so bad. Okay. Okay, here, 2, 2. So it's single or double. Oh, got an element by itself, element by itself. So aluminum replaces iron. This is a single replacement reaction. Here, I start with one substance and I break it down into 2, so I know it's decomposition. And here's another one of these tricks. See how I have a 3 oxygen here and 2 here? The only way to balance them, you guys can't just put a 1 here because you multiply the numbers. So what I would do is I would put a 3 here and a 2 here. And then another 2 here. So when you have, like I said, 3 here and 2 here, put a 3 here and a 2 here. That's the only way you can balance them out. All right. Here's another combustion one, carbon dioxide and water. Okay. So again, I'd put my 3 here, my 2 here, 4 here, excuse me, got to get 8. Oh, my mouse is. Okay. So if I have a 3 here, 3 times 2 is 6, plus 8 is 14. I put a 7 here. Okay. So carbon, hydrogen, then oxygen. That's the easiest way to do combustion. All right. So that's your types of reactions. And again, revisit that, review that if you're having troubles. Okay. Then we did empirical formulas. Okay. Let's say I have a substance that's 56.4% potassium, 8.7% carbon, and 34.9% oxygen. Remember, you take the amount they give you and then you divide by their mass from the periodic table. Okay. So you get, this gives you the moles. So I did that for all of them. I got this one, 8.7 divided by 12 and 34.9 divided by 16. And again, this mass comes right from the periodic table. So I get these moles. Then you set up a mole ratio with the smallest number on the bottom, which is this. So this number divided by the smallest is 2. This number divided by the smallest is 1 because it is the smallest. And then this one is 3. So I got 2 to 1 to 3. So there's my formula, K2CO3. All right. So again, you take their mass from the periodic table and divide. That gives you the number of moles and then set up your mole ratios. Here's another one. I have aluminum is 52.94% and oxygen is 47.06%. Okay. So I take my 52.94, divide by 27. That's the number that comes off the periodic table, 1.961. And then the same with oxygen, divide by 16 and get 2.94. When you divide them, you get 1 to 1.5. Remember, you can't round that. That's too much rounding. So I would double both of these, make this a 2 and this is a 3. So I'd get Al2O3. Okay, that's empirical formulas. All right, that's where you get the percent. And if you get it in grams, you guys, instead of percent, do it exactly the same way. There's no trick involved, okay? Okay, here's one where we're going to do molecular formula. Now, molecular formula, you find the simplest formula, and then you've got to figure out the mass. So first thing I do is I take my 74% carbon, divide by 12, get 6.166, that's my moles. I take my hydrogen, 8.7 divided by 1, gotta like hydrogen, 8.7. And then I take my nitrogen, 17.3 divided by 14. So here's my numbers. Then when I divide them, each number divided by the smallest, I get a 5 to 7 to 1. So here's my empirical formula. C5H7N. That's just what we did on the chart, the slide before as well. Okay, that's the empirical formula, simplest formula. Now it says the molecular mass, or the molar mass of nicotine is 162.1. Okay, so what I'm going to do then is I'm going to find the mass of this. Carbon, let's see, we got 60, 12 times 5 is 60, plus 7, 67, plus 14, what is that, 81? Okay, so I take the 162 divided by the formula mass, what this weighs, and I get 2. So all I have to do is double everything on here. So I make it C10, H14, N2. Okay? All right. That's how you do molecular formula. It's just one more step. Okay? Then we looked at stoichiometry, looking at mass relationships. Okay? So calculate how many grams of iron can be made from 16.5 grams of iron 3 oxide. Okay? So I've got a balanced equation. Remember, no balanced equation, can't do these problems. So I take what I know, 16.5 grams of iron 3 oxide. Remember, the 3 doesn't go here, it's up here. 1 mole, and this is its mass. Okay? If you wanted to use 160, that's fine, you guys. And then you do your mole ratio. Okay, this is moles of Fe2O3. So if you look here, that's a 1. And I'm trying to find how many grams of iron. So I'm going to put iron on top. And by my balanced equation, there's a 2. And then my last step is I want to change it to grams. So 1 mole of iron has a mass of 56. That would come right off the periodic table. So I take this, and I divide by this. And I get 11.57 grams of iron. So when I have 16.5 grams of iron 3 oxide, I can produce 11.57 grams of iron. If that isn't enough, then I got to add a bunch more iron 3 oxide. Okay? All right, here's another one. How many moles of oxygen are needed to produce 62.8 grams of water? Again, we got a balanced equation. Life is grand. Okay, so I write down what I know. 62.8 grams of water. Okay, I want to put grams of water on the bottom. 18. 1 mole of water on top. Okay, that's what it weighs. Remember, don't use your balanced equation. I wouldn't write 6 here. All I'm doing is converting grams to moles, so it's always going to be 1. The only time you use your balanced equation is when you do your mole ratios. So I put water on the bottom, and I'm trying to find oxygen. And it just says moles of oxygen, so I don't have to change it to grams, you guys. So I'm going to take 62.8 times 5, divide by 18, and divide by 6. And then you get 2.91 moles, okay? So that, again, be careful when you're doing your problem. Sometimes you just want to go grams to grams. You don't always have to do that. Sometimes the problem is. What I'm going to do is quit right here because I'm almost to the end, and then I will finish the review in another lecture. And, you know I'm not supposed to talk more than 15 minutes, but I want to go through this and make sure you have it. So I'll quit here, and then I'll finish up the review, and so there'll be 2 parts to this lecture. Okay? See you soon.